Good morning, class. Let's continue with the next practical session, which is data reduction. Understanding Principal Component Analysis, PCA. PCA is actually the first principal component. PC1 captures the highest variance in the data set, represent the direction of greatest variability, and the second principal component, PC2, capture the remaining variance, ensuring it's uncorrelated with PC1. Similarly, the subsequent components, PC3, PC4, and etc., capture the remaining variance with each being orthogonal, which is uncorrelated to the previous one. So we'll see how to implement this PCA in R. So we will perform the PCA on the empty car data set to reduce the dimensionality, visualize the variance, and explore the relationship between different car attributes. Okay, first of all, we need to install and loading the required packages for this. So first we install package called dplyr. Okay, and then let's install first. You can see here the red color. Okay, it means that it's still running, so it's over, it's done. You can see package dplyr successfully unpacked. And then now we need to call the package. Okay, how to load the package? Library dplyr. Okay, it has been loaded. Okay, loading the data set. The empty car data set is a built-in data set in R. It contains the data, fuel consumption, and various performance and design aspects of 32 cars. So this data set has 10 variables, including miles per gallon, MPG, horsepower, and weight. Okay, so let's see the structure of the empty cars. Okay, so you can see this is the empty cars. Okay, in order to see the complete data set, you guys can see here. Okay, it's still loading, or you can type view empty cars. So it shows here. Can you see? Okay, now let's continue to perform the PCA. To perform PCA, we use PRC computing function. Component function. It is used to scale and center the data before applying PCA. Since PCA is based on distance, measure, and scaling, ensure that all variables are treated equally. So it's perform principal component analysis, and then scale dot is equal to true, where the scales the data before applying PCA. Center true, so we want to subtract the mean. Red X is actually a return the transform data principal component. So all is true. So let's take this code and and then names PCA. So let's see what we get. So we got S, date, rotation, center, scale, and X. Okay, so if you click this, you can see here. Okay, it consists of the list of length is 5, S div, okay, standard deviation, and then rotation 11 by 11, center for 11, scale for 11, and X 32 by 11, because we have 32 observation. So the summary of my PCA, let's see why we need to do the summary. Okay, we need to identify the standard deviation for all the principal components that we obtain. Okay, we summarize the PCA model to understand how much variance is captured by each principal components. Okay, so principal components loading, we will see the weights loading of each variable in the principal components by using my PCA $sign with rotation shows the loading coefficient of the principal component. So what are the coefficient of the principal component? So you can see this is the output from the summary. Yeah? So standard deviation, proportion of variance, cumulative proportion. Okay, cumulative proportion is actually, okay, the first one we got 0.6008. The second one is 0.2409, right? So it's add up. 0.6008 plus 0.2409, you will obtain 0.8417. So it will be add up, that is cumulative, up to it reach 1. Okay. So let's see the my PCA rotation. Okay, so the principal component PC1, PC2, PC3 and PC4 with the MPG, cylinder and display, horsepower and drop. So that is the output. Let's see the components score, number 6. We will now inspect the scores, the values of the observation on each principal component by using my PCA $sign X provides a transformed data in terms of principal component scores, and the head display the first few rows. Okay, so let's see what we get from the answer. So it shows the answer for first 6 rows. Okay, for all the 11, how many components? Yes, total 11 components that we obtained, PC 11. So all the PC 11 here. So now we need to visualize the principal component. We will use biplot to visualize the principal components and their contribution to the overall variance. So biplot plots the principal component and their relationship, and scale is equal to 0. It's ensure that arrows are scaled to represent the loading. So biplot my PCA. So what we want to plot? We want to plot on my PCA. Main is equal to biplot of principal components with the scale of 0. So when we run for this R programming, you don't have to write like semicolon or comma at the end of the line of code. So can see here. Okay, let's try to zoom and see. So this is the biplot principal component. So you can see we have total 11 components, right? So basically it shows the correlations. Okay, it's trying to find the relationship. Okay, now let's go on with computing the standard deviation and variance. We will now compute the standard deviation and variance by using my PCA $sdiff displays the standard deviation of each principal component, and my PCA .var is variance. It's compute the variance of each component as well. Okay, so let's try this. Let me close this one. Okay, so you can see the standard deviation for all the components, all the principal components there. We have 2.5, 1.6, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because we have 11 components PC, right? Principal components. Same goes for the variance as well. Variance will be square of standard deviation. So the proportion of variance explained, we calculate the proportion of variance for each component and visualize it using scree plot. Okay, it's called as a scree plot. I guess it's correct. Yeah, to see how much variance in each principal components explained. So plot the proportion. X lab, Y lab is the label of X and Y, and Y limit type is equal to B, which plots both points and lines. So we have the proportion of variance for myPCA.variance over sum of myPCA.variance with the plotting of proportion. X label is principal component and Y label is proportion of variance explained. Y limit with 0, C01, the minimum value is 0 and the maximum value is 1. Type B, okay, which means both points in the line. Main is scree plot. So we want to plot the scree plot over here. Let's see what is the scree plots means. Okay, so you can see here, this is the plotting. So we have scree plot with variance, principal components, proportions of variance explained. So you can see that it almost, when it's reached like consistent level already. Okay, this one for scree plot, and we have another one, cumulative proportion. Okay, we can see the cumulative variance explained by the components. We have cumulative sum and then plot. So for this one, we have okay, it's like just a reverse of the previous one. Because one with standard deviation, the other one with variance. So choosing the top principal component, we can identify the smallest number of principal component that explain at least 90% of the variance, which cumulative sum proportion variance more than 0.9, and find the smallest number of principal component that explain at least 90% of the variance. So which cumulative sum proportion variance it shows more or equal to 0.9. So let's check principal component number 4. So you can see, so this one is the one that explain more detail as a principal component, PC number 4. Next, predicting with principal components. We can now use the first few principal components to predict another variable. For example, predicting the displacement from top 4 principal components. We create the data frame. You know what is data frame, right? It's like a table from the original variance display with the first 4 principal components. Train data, data.frame, display equal to empty cars. Which column do you want to select? Displacement. With myPCA principal components, you want to take from 1 to 4. Okay, the 4 principal, and then head of train data. So what we obtain, the first few lines of the data is shown here. So you can see for Mazda, these are the 6 records. First 6 record with the display and the principal components values. So building a decision tree. Next, we can use the R-Part package to build a decision tree model to predict displacement using the first 4 principal components. Okay, R-Part is actually fits a decision tree model. Displacement, the formula for predicting displacement using all the other variable principal components in this case. So data equal to train.data, specify the data used for fitting the model. Method will be ANOVA. For model is regression. And then R-Part.plot will be decision tree. So for that we need to install package got R-Part and then R-Part plot, and then after we install we need to call the package as well. So otherwise we cannot draw the decision tree. So let's wait until it's completed. You can see the red color button here. You can see my cursor. It will stop once it's completed. So we have to wait for a while. It won't take longer time usually. Okay, so the package was called. Okay, now we try to create a model. R-Part model. Okay, let's enter. So this is the tree. You can see principal component 1 with less than 0.68. Yes, it's 136. And 353, which is with 44%. So basically this practical part, it shows you PCA, which is applied to empty cars data set, visualize the principal components and use them to predict car displacement with a decision tree. So this helps us to simplify the data and reveal the patterns that would have been difficult to see in the original high dimensional space. So we have a multi-dimensional space there, so it's very hard to see. So once you reduce, so the dimensionality reduction will help you to see this. Okay, the next one will continue with it's a TSNE. It's a non-linear dimensionality reduction technique that is particularly effective for embedding high-dimensional data into a space of 2 or 3 dimensions. So the core idea of TSNE is to model the similarity between the data point in a high-dimensional space and project these similarities into a lower dimensional space. So it achieves this by minimizing the divergence between 2 distributions. One measure pairwise similarities and the other one measure pairwise similarities of the corresponding low dimensional. One is high dimensional, one is low dimensional points. So non-linear mapping, unlike linear dimensionality, PCA is actually for linear dimensionality reduction, but TSNE for non-linear relationship data. Okay, so let's see. Okay, for this one we need to again we need to install the library. I don't know whether this library is already installed or not. Okay, let's see. Okay, I think I can clear the console. So you can see here the broom. So just click. Okay, there's no package called this one. So install package called RTSNE. Why the package is unable to install. Okay, I forgot to open and close code. Okay, it's successfully installed. Next, we need to install the ggplot. Okay, if ggplot is not installed, you have to install. The method is the same. Here, ggplot2. So if the package is installed, you can see here under packages. Okay, just now we installed dplyr, right? It's here. ggplot2, it's here already. It's okay, it's still loading. And then previously we installed what? rtsne. Let's go to here. Okay, so we need to wait because there is a red line, red symbol here. And in this TSNE, we want to utilize data called iris. Okay, iris dataset. So we want to prepare the data, convert the data to a matrix, and remove the species column, which is not needed for TSNE, and remove any duplicate records or rows to avoid errors during TSNE computation. Ensure the results are reproducible by setting a random seed. Iris is actually a flower. Okay, I guess it's downloaded, is complete. So now we can call the libraries and call the data as well. Let's copy. Okay, it's called already. And then let's back. Step 2, prepare the data. So we need to convert as already. So remove the species column for TSNE, and then remove the duplicate records. Okay, so in order to make a comments in R, we just use hash symbol and write the comment. Okay, maybe you have a question in your mind. Why don't I write this one as a script and run? Also can. Okay, you can write, for example, R script, all the coding that we have run under your console here. You guys can copy paste and run as one script also can. No problem. It's still working. Okay. Object SNE is not found. What is this? Okay, I know, because the column is the TSNE has been separated. Let me check on this. Okay, let me copy here. It should come up. Okay. Let's try again. Okay. So you can see the iris data set with 150 observation and iris matrix. Okay, the previous iris with species column. After we remove the species column, now we have the matrix without the species column. The last column, column number 5, is removed. Okay, so step number 3, we perform TSNE. We just need, it's already built-in algorithms. You just need to call the algorithm and run. Okay, run the TSNE algorithm. On the prepared data, we specify parameters. So we need to specify TSNE result, TSNE iris matrix, because we want to remove, we already removed the species column. So we have to use that particular data set. Dimension 2, perplexity with 30, verbose, true, maximum iteration is 500, and the TSNE result. I guess, let me just bring up my scat later, got error again. Okay, so you can see here for all the records, cause sometimes if the output is too long, the previous coding part under your console will be, you might lose it. By the way, we have 149. Okay, and then so the first part of the log indicates the PCA principal component was performed before running the TSNE. So it's common pre-processing step to reduce the noise to improve the performance of TSNE. Yeah? After that, you guys can see this is a common pre-processing step. Okay, I already explained. However, the log doesn't show explicit PCA results. So it's likely part of TSNE internal process. It's already internal. We didn't see the PCA explicitly. So it's reduced the dimension to 2. Perplexity 30 balances local and global aspects of data. Verbose is actually pre-in-progress messages, and maximum iteration with 500 set of iteration. Step number 4 and 5, I think we need to visualize. Yeah. Okay. Step number 4, create data frame with TSNE original species label and store the TSNE result in a data frame. Add the species label to TSNE and ensuring they match the reduced data set, no duplicates. So for that, we have data set. We create a data set data frame from the result, because we have TSNE result, right? You can see here. Now you can see here this one, TSNE underscore result. Okay. And we want to create a new column called Y, and then with the species, iris data set species. So we are referring to iris data with the species, and duplicated, we need to delete. The column name will be TSNE data with dimension 1, dimension 2, and species. Okay, let's try these. So can you see dimension 1, dimension 2, species. Originally there are 150 records, right, in iris. You see, original 150, but it's become 149. Might be there is a one record which is repeated duplicate record, which is we already reduced previously. So step number 5, we just need to plot the TSNE result with ggplot. Okay, why we call or install the ggplot library is actually for plotting function. Okay, so you can use geometry point, the labels for the title, X label, Y label, and then the team minimal. So let's see the result. I hope there's no error. Okay, never mind. Let me just bring up this. I worried that it got error again. So bring here. It's too big, so that's why. Okay, so you can see the result of dimension 1. Okay, let me zoom it. So we have 3 species. So basically TSNE is actually a tool for visualizing the high dimensional data, providing the hidden complex data set. So by preserving the local and global structure of data, TSNE facilitates the discovery of patterns and clusters. So when you implementing TSNE in R, is very straightforward with the package called RTSNE. When combining it with advanced visualization technique, can significantly enhance the interpretation. So whether in genomics, NLP, finance or other field, TSNE continues to be a valuable technique for data scientists and researchers, especially for biological data sets, because they are more to non-linear type of data sets. Okay, that's all for data reduction. We'll continue for data transformation in next practical. Thank you.